Back with the Fresnel integrals, but this time we're going to solve them using the coolest integration technique in existence, that is Feynman's technique. And we're going to make use of two particular tools in this case. We're going to make use of Euler's formula, which states that if you have e to the I times some real number t, this equals the cosine of t plus I times the sine of t. And now how does that relate to the integrals that we have? Notice that we have the cosine and the sine of x squared. So we can define a complex number e to the ix squared, which equals, using Euler's formula, the cosine of x squared plus I times the sine of x squared. So we'll be interested in the integral of this complex function of x from negative to positive infinity, and we'll apply Feynman's technique to this function, to the integral of this function anyway. So basically we're interested in, call it I, the integral from negative to positive infinity of e to the ix squared with respect to x. And we're going to use Feynman's technique, meaning that we're going to have to define an integral function I of some parameter t, right? And before we do that, let me explain that in this case, for this particular case, we're going to use the general form of the Leibniz rule. Now, what does this general form of the Leibniz rule state? It states that if you differentiate with respect to the parameter t some integral from a to b, where a is a function of the parameter t, as is b. So the limits of integration in this case, in the general case, are functions of the parameter t with respect to which you're differentiating. Now, sorry about that. So the integral from a to b, where a and b are functions of the parameter of some function of the variable x and the parameter t, and integration is carried out with respect to x. This equals the integral from a to b of the partial derivative with respect to t of the function plus the function evaluated at the upper limit b times the derivative of b with respect to t minus the function evaluated at the lower limit a times the derivative of a with respect to t. Now that that's clear, we can move on towards defining our integral function I of t. Now before we do that, first up, notice that the integrand is an even function with respect to x. So we could just integrate from 0 to positive infinity and double the result. So let's define our integral function around this integral in white, the integral from 0 to infinity of e to the ix squared. So what I'm going to do here is define a weird integral function. I'm going to define I of t as the square of the integral from 0 to t of e to the ix squared with respect to x. So in this case, I've introduced the parameter as a limit of integration. In this case, it's the upper limit. And I've introduced a square term. I've introduced the square of the integral, and the utility of this will become clear in just a few moments. So now when I differentiate with respect to the parameter t, first up, I'm going to have to use the power rule. And using the power rule, I have twice the integral from 0 to t of e to the ix squared, integration with respect to x, and I have to multiply it by the derivative of whatever is inside that square, meaning that I'm basically just using the chain rule, right? First apply the power rule and then apply the derivative to whatever is inside the exponent. So just using the chain rule here. Now, applying the general form of the Leibniz rule, I have the integral from 0 to t of the partial derivative with respect to t of e to the ix squared. Now, notice that Since we're differentiating partially with respect to t, the x is a constant. So you're differentiating a constant with respect to t, so you're going to get 0. Correct? Next up, we have to add to it the function evaluated at the upper limit, and the upper limit is t. So e to the x equals t, which means you have e to the I t squared times the derivative of the upper limit with respect to the parameter, minus the function evaluated this time at the lower limit, which is 0, times the derivative with respect to the parameter of the lower limit, which of course is 0 anyway. So, and the derivative of t with respect to t is 1. So all you get here is a term e to the I t squared. And yeah, this is sort of what you'd get if you just apply the fundamental theorem of calculus and complex analysis to the derivative of this integral function. So yeah, but using the Leibniz rule provides a cool insight into the actual mechanics of the differentiation carried out. So you have twice this term e to the I t squared times the integral from 0 to t of e to the I x squared dx. Next up, notice that we're integrating with respect to x, right? And this exponential term outside the integral is independent of x, so you can just slip it into this integral, and you now have 2 times the integral from 0 to t of e to the I x squared times e to the I t squared dx. And of course, we can write this as e to the I x squared plus t squared. Now, what am I going to do next? Well, first up, I'm actually going to factor out this t squared term. I'm going to factor this out, then perform a substitution to make our lives much easier. So we have e to the I t squared factored out, and you're left with x squared by t squared plus 1, integration with respect to x, of course. Now, what was that substitution that's going to make our lives much easier? Well, for that, consider this term here, this x by t term, and you let x by t equal some other variable, say y, which of course implies that dx equals the constant t, because in the x world, the parameter t is just a constant, right? So we have dx equal to t times dy, by which we can write the derivative of I with respect to t as twice the integral from, now as x approaches 0, y approaches 0 as well. But as x approaches t, x by t approaches t by t, which is 1. So we have twice the integral from 0 to 1 of e to the I t squared times, I'm going to write this as 1 plus y squared times t integration with respect to y. Okay, now we're going to do something extremely cool. We're sort of going to reverse the Leibniz rule here. Now, recap. The Leibniz rule was all about differentiating with respect to the parameter t. So let's turn our attention towards our parameter t, and notice that we have a t squared term up here and a t variable down here. So if I just slip this 2 inside the integral, then I have 2 times t, which is very conveniently the derivative of t squared. And if I have the imaginary unit here as well, but you know what, forget it, that's just a constant anyway, we'll turn our attention there later. So anyway, we have 2 times t, which is the derivative of t squared, and by the Leibniz rule, we're differentiating with respect to the parameter, right? Now, if we're differentiating partially with respect to the parameter t, this 1 plus y squared term is a constant. And don't forget the imaginary unit. The imaginary unit is a constant as well. So what if we take everything inside the integral and we just very innocently write this as the partial derivative with respect to t. I think by now you see where I'm going. Of e to the it squared times our constant in the t world, 1 plus y squared, divided by the constant I times the other constant, 1 plus y squared. So we have this partial derivative here, and our integration is with respect to y. Now that was smooth, extremely smooth. And it gets even better. It gets even better because if you switch up the order of the integration and the differentiation operators, now remember in the start, when normally you use Feynman's technique, you have the total derivative with respect to t of some integral. And when you switch them up, this total derivative is converted into a partial derivative. But now you're performing the reverse switch up, right? You have the integral of a partial derivative. So once you perform that reverse switch up, you will get a total derivative on the outside of the integral from 0 to 1 of e to the it squared times 1 plus y squared divided by I times 1 plus y squared, integration with respect to y. So on the right-hand side, you have a total time derivative, and on the left-hand side, you had the derivative of I with respect to t. So if you integrate with respect to t on both sides, you'll have the function I of t equal to the integral from 0 to 1 of e to the it squared times 1 plus y squared divided by I times 1 plus y squared dy plus the constant of integration. Once again, that was awesome. Amazing. Anyway, so now we have to figure out the value of this constant of integration. And for that, let me just write out the left-hand side. Now, the integral function was the square of the integral from 0 to t of e to the ix squared dx, right? So this was our integral function, and this equals this integral. I'm just going to write this up here to avoid all that work. So the left-hand side was the integral from 0 to t, e to the ix squared dx, and a square on all of this. So I need some information to figure out the constant of integration. I need to know what my function, what value my function had at some value of the parameter t. And a very wise choice here would be to plug in t equals 0, because now you have an integral from 0 to 0, which is 0, of course. So this implies that I of 0 equals 0. So on the left-hand side, you have 0 equal to the integral from 0 to 1, 1 by I out here. Do not forget this term. And this is e to the I times 0 squared. So all of this is a big fat 0, and e to the 0 is 1. So you have 1 plus y squared. And this is quite easy to evaluate, right? This is the inverse tangent of y with the limits being 0 and 1. So the inverse tangent of 1 is pi by 4, right? And the inverse tangent of 0 is just 0. So this equation implies that the constant of integration equals negative pi by 4 times 1 by I. And 1 by I equals negative I, right? So just write this as positive pi by 4 times I. So that's your constant of integration. So coming back to our equation was I of t, or just writing this in the expanded form, integral from 0 to t e to the ix squared dx squared equal to 1 by I times integral from 0 to 1 of e to the it squared times 1 plus y squared divided by 1 plus y squared integration with respect to y plus this constant of integration that is pi by 4i. And let me just write this in a more neat manner. Sorry, my handwriting is definitely never going to improve. But thankfully you understand what I'm talking about anyway. So now let's take a moment to remember exactly what we were after. Our interest was the integral from 0 to infinity of e to the ix squared, right? Which is exactly the limit of the integral from 0 to t of e to the ix squared dx as t approaches infinity. And for this limit here, we're going to have to first take the square root here. We're going to have to take the square root to get rid of the square, and then evaluate the limit as t approaches infinity. So square rooting both sides of the equation and studying the limit as t goes to positive infinity, what do we get? What exactly do we get? Well, first, let me just get myself some writing space. Now, this is where flammable maths actually messed up. He messed up over here. Although he used the negative version of this exponential function, so he had something that looked like e to the negative it squared plus multiplied by 1 plus y squared, yada yada. Anyway, so you don't need the negative sign here, because either way, whether you have a positive I or a negative I, it's still going to be an oscillatory function, because by Euler's formula you have a cosine term and a sine term. So you can't say anything definitive about the behavior of the function as t goes to infinity. It doesn't approach anything, right? It doesn't approach anything. So this structure of the integral is actually pretty cumbersome. It doesn't give us any information about what happens as t goes to infinity. And to understand what will happen as t goes to infinity, I'm going to have to consider this separately for a moment. And I'm going to use a clever substitution to actually uncover its behavior as t goes to infinity. And it does indeed converge. That's the good news. It does go to 0 as t goes to infinity. But how do we prove that? Well, for that, you have to let y equal to x by t, which implies that dy equals 1 by t times dx. So what does this substitution actually do for you? Well, replace the y by a 1 by t, you replace the dy by a 1 by t times dx, and you replace these y squared terms by x squared by t squared terms, So now taking the limit as t approaches positive infinity, we see that these terms go to 0. So you have a 1 plus 0 down here and a 1 plus 0 up here. That still doesn't give us any useful information. But this term over here, this is our savior. As t goes to infinity, 1 by t approaches 0, which is awesome. So you have 0 multiplied by all of this stuff, which is 0, which proves that the integral does indeed go to 0 as t goes to infinity. So that means what I can do now is that I can write, now this left-hand side was I of t, right? And this equals the square root. All of this is just a 0, and you're left with pi by 4 times I. Now that is awesome. That is extremely cool. So what I'm going to do now is I'm going to separate this into real and imaginary parts. So you have square root pi by 2 times the square root of I. And the square root of I can be evaluated quite easily using the polar form of complex numbers. So this is just I to the 1/2, right? and I is just e to the I pi by 2, and it's being square rooted. So you have square root pi by 2 times e to the I pi by 4, and using Euler's formula, this is the cosine of pi by 4 plus I times the sine of pi by 4, and both evaluate out to 1 by the square root of 2. So you have square root pi divided by 2 times square root 2, which is in fact the square root of 8. So write all of this as square root pi by 8 plus I times the square root of pi by 8. And all of this equals the integral from 0 to infinity of e to the ix squared dx. And again, using Euler's formula, you may conclude that the integral from 0 to infinity of the cosine of x squared with respect to x equals square root pi by 8, which is also equal to the integral from 0 to infinity of sine of x squared with respect to x. And that was absolutely amazing. This was awesome. This is definitely the coolest way to evaluate the Fresnel integrals, and that definitely deserves a like and subscribe. So be sure to do that. Thank you. See you next time, and stay tuned for the next video where I'm going to integrate under the integral sign, which is also extremely cool, by the way, to solve the Fresnel integrals. Oh, and in case you just want the case where you're integrating from negative to positive infinity, you know the drill. Just double the result because you're integrating even functions. So anyway, again, thank you. See you next time.